Hello everyone, my name is Aslan Mojallal and I am a Senior Power Engineer and R&D Manager at ETAP. In today's energy landscape, the role of power plant controllers or PPCs is crucial. As a vital part of the SCADA and control solution, PPCs regulate and control inverters, energy storage systems, generators, capacitor banks, and the other equipments of a renewable power plant. PPCs ensure that plant behaves optimally at the point of interconnection, or POI, in terms of production levels, revenue, compliance, and grid stability. With the increasing penetration of renewable energy, the demand for reliable and accurate control systems has never been higher. Given the diverse designs of renewable plants, a flexible PPC solution is essential, particularly for hybrid plants. The ability to rigorously study and validate these systems prior to deployment adds immense value, ensuring PPCs meet the unique demands of each plant while supporting the broader goals of energy transition. The conventional technology for power plant controllers often relies on PLC-based solutions. These controllers are well suited for simple plants with basic control logics, offering reliability and ease of use in straightforward applications. However, as the complexity of renewable power plants increases, particularly with integration of hybrid systems, the limitations of PLC-based solutions become apparent. These solutions struggle to handle the sophisticated control requirements of hybrid plants, such as managing multiple points of interconnection or implementing advanced functions like virtual inertia and damping. This makes PLC-based systems less adaptable to the evolving needs of modern renewable energy projects. Therefore, customers in renewable energy sector are increasingly facing challenges with their power plant control systems. Many are working with PLC-based solutions which, while effective for simpler setups, are beginning to show limitations as plants become more complex. For example, customers often struggle with the integration of multiple types of generation assets such as wind, solar, and energy storage within a single cohesive control system. This is especially true for plants with multiple points of interconnection, where coordinated control between different zones is critical. Reliability is another major concern. Customers require solutions that they can trust to operate without fail, even under the most demanding conditions. This level of dependability often necessitates extensive pre-deployment studies, along with the robust hardware and software redundancy, which can be difficult to achieve with existing PLC-based systems. Finally, the customers are looking for solutions that simplify the complexity of a power plant controller. They want solutions that are not only powerful but also easy to deploy and configure, reducing both the time and costs associated with bringing a new plant online. The ability to rapidly adapt to new requirements is increasingly seen as essential, but this is something that traditional PLC-based solutions may not fully support. Our ETAP solution, the ePPC, sets a new standard in the power plant controllers by directly addressing the challenges that traditional PLC-based systems often face. At its core, ePPC is a software-based solution which allows it to execute complex and sophisticated logics that are crucial for modern power plants, particularly those with hybrid configurations. One of the key strengths of ePPC is its model-driven nature. This feature not only enables rapid and error-free deployment, but also ensures that the controller is perfectly aligned with the digital twin of the power plant. By integrating closely the ETAP's robust simulation environment, ePPC allows for thorough testing both in software-in-the-loop and hardware-in-the-loop configurations before any real-world deployment. This level of testing and validation significantly enhances reliability and helps avoid costly errors once the system is live. Additionally, ETAP simulation software offers critical study types like grid code compliance studies and transient stability analysis, which complement EPC's capability and ensure that the entire system is well prepared for operational challenges. Reliability is further reinforced by ePPC support for both software and hardware redundancy. This means that in the event of an unexpected failure, the system remains operational, ensuring continuous control, which is vital for power plants where downtime is not an option. ePPC also excels in providing fast controlled response times, enabling quick and precise adjustment to shifting grid conditions. The inclusion of advanced functions such as frequency and voltage support is particularly important for maintaining grid stability, especially in the face of fluctuating renewable energy inputs. These capabilities further enhance the overall performance and reliability of the power plant, making ePPC a future-proof solution for renewable energy projects. Another key feature of the ePPC solution is its software-based nature, which supports agile development and allows it to be tailored to any specific power plant project. Being model-driven, ePPC significantly reduces human error throughout the entire process, from design to final deployment. This ensures that the solution is closely aligned with the power plant's digital twin, resulting in a more reliable and efficient performance. Our model-driven solution offers a seamless journey from the design of a power plant to its full-scale operation and control, all within the ETAP environment. It begins with the design phase, where every component in the plant, whether renewables, transformers, or capacitor banks, is meticulously modeled in the ETAP. This comprehensive modeling includes not just the physical attributes, but also the settings and operational capabilities of each element. Various ETAP modules, such as load flow, transient stability studies, are employed to accurately size the assets, ensuring that they meet the demands of the plant. Grid code studies are also conducted within ETAP at this stage to verify that the plant complies with all necessary regulations.
Now, let's walk through how this works. The first step is to model the electrical system using ETAP's one-line diagram or OLB. To begin, we need to be in the base revision and in edit mode. ETAP provides a wide variety of electrical elements that may be part of your project, making it possible to build an accurate representation of the system. You can also adjust the level of modeling detail for each element depending on the goals of your study and the needs of the project. Once the electrical model is complete, we can then add the primary controllers, the POM meters, and the gateway controller. This part of the workflow is usually very straightforward. Each controllable generating unit requires its own dedicated controller. So, for example, each PV unit will have a PV controller. The same idea applies to the wind turbines, battery energy storage systems, and other controllable assets. For every point of interconnection to the grid, we also need a POM IED. This device serves as the meter at the interconnection point, measuring active power, reactive power, voltage, and frequency, and then sending the information to the power plant controller. So in this example project, since we have two utility interconnection points, we also have two POM IEDs. And in addition to those devices, every PPC model includes a single gateway controller. ETAP also provides several useful tools to support this modeling stage. For instance, if you want to verify compliance with the grid code requirements, you can define those requirements in the rulebook. You can access the rulebook under the Rules section in Capability and Control. right through, along with the available rule definition. ETAP allows you either to use a predefined rules or create custom rules for your own project requirements. For example, here we have a rule book that defines write-through capabilities such as LVRT, HVRT, LFRT, and HFRT. You can also define the capabilities of your equipment such as inverters and other plant assets. ETAP includes built-in example, but it also gives you the flexibility to create your own capability definition and grid code requirements. Another important feature at this stage is the ability to add generation and load profile when using the time domain load flow module or TDLF module. This allows the system load and generation to follow a time-based profile that you define. You can either enter your own profiles or use the profile libraries already available in ETAP. These profiles can be accessed through the library and then profile library, where you can select from a wide range of predefined options or modify them as needed. Finally, if you want to study system behavior under fault conditions, you can use other modules like transient stability or STAR-Z or different modules that deal with these kind of studies. This allows you to simulate fault at different locations in the network, evaluate their impact on the system, and observe how the controller responds to these events.
Once the model is built, the next step is to integrate the controllers, including our ePPC. Thanks to the model-driven nature of ePPC, this integration is smooth and automatic. When an element in the project is associated with ePPC, all its settings and connectivity are instantly transferred to the controller, making them available for the logic setup. This ensures that the controller is perfectly aligned with the rest of the plant's model.
This is done by selecting the controller element from the instrumentation section in the edit toolbar and placing it in the project. To load the controller logic, we open the controller, navigate to the DLL page, and click on the import button. This opens the ETAP folder where the controller logic is stored. From there, we select the ePPC OTI controller DLL, and ETAP loads the logic and the settings required for the power plant controller. Once the DLL is loaded, the next step is to associate the relevant devices with the ePPC. To do that, we navigate to the Associated Devices page and assign the elements that the ePPC will monitor and control. The ePPC primarily interacts with the power plant level and unit level controllers rather than directly with the elements themselves. For example, the ePPC communicates with the PV controller, and that PV controller then controls the corresponding PV unit. So in this configuration, the PV controllers should be associated with the ePPC. In our demonstration project, we have several PV units and WTG units along with their corresponding PV and WTG controllers, 2 battery energy storage systems, 2 STATCOMs, 2 POM meter, and 1 gateway controller. All of these relevant elements should be assigned on the Associated Devices page of the ePPC. By associating these elements, their settings and model information are automatically transferred into the ePPC environment without requiring manual reentry. This is one of the major advantages of ETAP's model-driven structure, since it improves both the efficiency and ease of use while reducing the chance of configuration errors. Within the Associated Devices page, we should enable the monitor option for any device from which the ePPC needs to read the measurements. Similarly, we should enable the control checkbox for any device that ePPC is expected to send commands to. These settings are especially important for hardware in the loop or HIL testing, as well as for the field deployment, because enabling or disabling these checkboxes affect the input and output and DMP3 tag assignment. And with that, the ePPC model is fully integrated in the project model. Overall, this is a very straightforward process and a good example of how ETAP streamlines controller integration within a model-based workflow.
The next step is setting up the necessary logic in ePPC. An ETAP can be used to simulate and monitor the controller's behavior to ensure it functions as intended. This step is crucial for validating the system before deployment. When it's time to move from design to deployment, the logic can be easily uploaded to the ePPC hardware through a straightforward process in ETAP. Configuring the communication settings and deploying the logic takes just a few clicks, making the transition from the design to operation both efficient and error-free.
As discussed previously, this is done from the DLL page of the ePPC controller editor. At the device level, we define some of the basic functionality and operating settings of the PPC. For example, we specify whether the controller is enabled, what is the execution rate, and whether the simulation is running in the software environment or in a hardware-in-the-loop environment. These settings do not define the detailed control functions of the PPC. Instead, they represent more general device-level settings that apply to the controller as a whole. At the system level, we define broader plant-level settings for the ePPC. For example, if the POM meter arrangement includes redundancy, that should be defined here. If the project uses a specific rulebook for the capability requirements of the overall plant, that also needs to be assigned here. And if the primary assets or generating units have specific capability requirements, those can be configured in the ePPC settings as well. The general settings section covers the more common plant-wide parameters. For example, this is where we define the plant-based values, which can either be entered manually or calculated automatically by the ePPC. This section also defines how PPC should behave during abnormal system conditions, such as faults, and how it should respond if one of the devices become undispatchable. These types of overall operating behaviors are configured under the general settings. Next, let's talk about core functionalities of ePPC. The first one is active power control. Active power control uses a PI controller to regulate active power at the point of interconnection. It also includes a ramp rate limiter to control the rate of active power change at the POM. In addition, it supports dispatch priority settings for hybrid plants. This is especially important in hybrid plants where different assets may need to be dispatched with different priorities depending on operation objective. It can also provide group-based frequency support, adjusting output power in response to grid frequency fluctuations. Next, we have reactive power control, which is similar in structure to active power control because it also uses a PI controller to regulate reactive power at the point of interconnection. Reactive power control regulates one of the three variables at a time: reactive power, power factor, or voltage. It also supports a group-based QBS scheme which adjusts reactive power in response to voltage fluctuations. Unlike active power control, it includes a ramp rate limiter to limit the rate of change at the point of interconnection. Another important function is renewable smoothing, which uses battery energy storage system or BESS to reduce fluctuations in renewable generation. The ePPC offers three methods for this function: moving average, Gaussian filter, and ETAP ramp rate limiter. This gives the user the flexibility to choose the approach that best fits the application and the desired plant response. Another available function is soft start and soft stop of the plant. This functionality provides a smooth startup and shutdown sequence based on commands from the operator, typically issued through the HMI. It can also automatically open or close breakers as needed, depending on the plant configuration and the settings selected by the operator. We also have energy shifting, which supports energy arbitrage using the BESS. In this mode, the operator provides a schedule that defines when the battery should be charged and when it should be discharged during specific hours of the day. Based on the schedule, the ePPC dispatches the BESS accordingly, allowing the plant to shift energy over time to support operational and economic objectives. These are some of the main ePPC functionalities that users typically configure for a project.
During the operational phase, ETAP's SCADA solution is used to manage the plant. An HMI is developed based on the plant's model, with ETAP SCADA acquiring real-time data from various sources such as breakers and meters and displaying this information on the controller center's HMI. This data is also fed into ePPC, where the internal logic, controller settings, and commands from the operator or higher layer controller layer are processed. ePPC then generates the necessary commands, which are relayed back to SCADA and subsequently sent downstream to relevant assets. Simultaneously, the HMI displays the updated information, raises any alarm or notifications, and logs all transaction and data for future analysis. This integrated, model-driven approach ensures that every step from design to operation is handled within a unified and highly reliable environment, reducing the potential for error and enhancing overall efficiency.
The final step in the process is hardware in the loop or HIL testing, along with SCADA integration and deployment. This step is what allows us to verify that the control logic developed in ETAP works correctly when connected to real-world systems. ETAP can operate as a real-time simulator, meaning it can continuously exchange live measurement and control commands with the deployed ePPC hardware. This is especially valuable before field deployment because it lets us validate behavior and fine-tune the controller logic in a safe and controlled environment. To enable this mode, we first switch to the simulation mode from normal to HIL test. This changes the simulation into real-time operation, so data is processed and exchanged at the same pace as it would be in an actual plant. The next step is to configure the DMP3 communication settings, including parameters such as the IP address, port number, and other communication options required for the protocol. This allows ETAP to communicate directly with the external ePPC hardware and exchange real-time data just as it would in a live deployment. Once the HIL configuration is complete, we can deploy the control logic. This is done from the associated devices page by clicking the deploy button. ETAP then automatically generates a deployment file with a .ePPC or .mgc extension. This file contains the control logic and configuration needed for the ePPC to run properly. At the same time, ETAP also generates an Excel file listing the I/O assignments. This file is very useful because it clearly shows how the controller will interact with the plant, including what measurement it reads and what commands it sends. After that, the deployment file needs to be uploaded to the ePPC hardware. There are two main ways to do this. The first is through the web client, which provides a browser-based interface for uploading the logic, managing the hardware, restarting the controller, updating the configuration, and performing cleanup tasks. The second is through the ICE Explorer, which offers more advanced tools for uploading, monitoring, and troubleshooting the controller. Both methods support deployment and allow us to observe how the ePPC behaves during real-time operation. Once deployment is complete, the ePPC starts operating in real time. It connects to the DMP3 server and continuously receives measurements either from SCADA or from ETAP real-time simulator. Using the logic we configured earlier, the ePPC processes those measurements, performs its internal calculation, and sends control command back to SCADA or directly to the plant. At this point, the control loop is closed. The ePPC is now actively managing plant operation in real time, helping optimize the performance and maintain compliance with the grid code requirements. It also communicates with both the HMI and SCADA, giving full visibility into system behavior as the plant runs.
Now let's dive into the built-in functions of the ePPC solution, which are designed to handle the complexities of modern power plants with precision and efficiency. These functions fall into three categories: active power and frequency control, reactive power and voltage control, and renewable smoothing by energy storage. First, let's talk about active power and frequency control. ePPC excels in managing active power and frequency through a sophisticated control loop. It ensures that renewable resources, generators, and energy storage systems are dispatched effectively to meet the set point of the plant's point of interconnection. This function not only tracks the set point, but also provides frequency support using a droop curve, which helps maintain system stability. Additionally, ePPC can implement virtual inertia and damping, which are crucial for stabilizing the grid. Ancillary features such as soft plant shutdowns are also included to enhance operational flexibility and safety. Next, we have reactive power and voltage control. In the reactive power and voltage control loop, ePPC manages various resources such as STATCOMs, capacitor banks, and renewables to regulate reactive power, power factor, and voltage at the point of measurement. This regulation is achieved through either uniform dispatch or a priority-based dispatch. The solution also supports droop-based voltage control, which helps stabilize the grid voltage. Importantly, ePPC considers the reactive power capabilities of each asset during dispatch, ensuring optimal performance and stability. The last built-in function is renewable smoothing by energy storage. To address the inherent fluctuations in renewable generation, ePPC utilizes energy storage systems to smooth out these variations. By dispatching energy storage systems in tandem with renewable assets, ePPC enhances the uniformity of combined generation, reducing fluctuations and ensuring a more stable and reliable energy output. Overall, these built-in functions of ePPC provide comprehensive control and optimization capabilities, making it a robust solution for managing the diverse and dynamic needs of modern power plants. When it comes to modeling hybrid power plants, ETAP offers a comprehensive and detailed suite of elements especially designed for such setups. ETAP includes extensive modeling capabilities for components such as wind turbine generators, photovoltaic arrays, inverters, generators, switch capacitor banks, and the STATCOM devices, and so on. Each of these elements can be configured according to their specific technical specification. For instance, settings like voltage levels, capacities, and operational parameters can be accurately inputted through ETAP's intuitive editor, library, and rulebook features. This allows for precise modeling that can greatly enhance the accuracy of various studies conducted within the platform. After integrating these elements into the model, primary controllers and the point of measurement or POM meter can be introduced. Primary controllers are essential as they manage the control of individual power sources. Their main role is to translate commands from secondary controllers like ePPC into actionable control signals for electrical components. For example, they might convert active or reactive power set points into inverter currents or exciter and governor control signals. ETAP also provides a unique controller for the POM meter, which is needed for collecting all necessary measurement at the point of interconnection. This data then is passed to ePPC, ensuring that it has real-time access to vital metrics needed to manage the power plant effectively. Once these controllers are integrated, the next step is to incorporate ePPC into the project. This involves associating the primary and meter controllers with the ePPC and granting it access to the settings and operational parameters of all relevant electrical components. At this stage, the system is nearly ready for simulation and software-in-the-loop testing. However, before initiating these tests, the settings within the ePPC need to be configured according to the specific requirements of the power plant project. This customization could involve setting up sequential dispatch for asset management in one project or configuring renewable smoothing function in another. The flexibility and depth of ETAP modeling capabilities makes it possible to tailor each project to its unique operational needs, ensuring that ePPC can perform its role with precision and efficiency. Let's walk through how to set up the simulation for ePPC. One of the primary tasks for ePPC is to track set points that typically originate from the system operator, often through the HMI in the control room. When working within ETAP simulation, particularly in versions prior to ETAP 2024, these set points were generated using a unique controller called the gateway. However, with the release of ETAP 2024, the process has been made more efficient. Now, the user can directly implement these commands as events within the event page of the time domain load flow or transient stability modules. This means you can easily schedule commands like active power, reactive power set points, or operational modes at specific times during the simulation. This approach not only simplifies the process, but also allows for more precise control and testing of how ePPC will respond to these commands during real-world operations. To prepare for deployment in the field, the final step is to deploy the logic and settings from ePPC and conduct hardware-in-the-loop testing. HIL testing requires a real-time simulator, which can be ETAP or another compatible simulator. Deploying the logic is straightforward. Simply click the Deploy button in the associated page of ePPC Editor. This section generates a package containing all the ePPC settings and logic. The logic can then be uploaded either through controller's web client or using a specialized ETAP application designed for this purpose. This application allows you to upload, manipulate, and monitor the real-time operation of both the controller hardware and the simulator. Once the deployment file is uploaded to the controller hardware, all necessary inputs and output tags are generated as DMP3 master, ready to interact with the ETAP simulator as the DMP3 server for the HIL testing. Once the HIL results are confirmed to be satisfactory, the hardware and logic can be shipped to the field for integration with the SCADA system. To conclude, let me recap the key aspects of our ePPC solution. Our advanced power plant controller stands out by addressing the limitations of traditional PLC-based systems with a modern software-based approach. This flexibility allows it to effectively manage complex hybrid power plants with multiple points of interconnection with seamless efficiency. One of the standout features of ePPC is its model-driven design. This solution not only accelerates deployment, but also minimizes human error by ensuring that every stage of development aligns precisely with the digital twin of the power plant. The ability to conduct comprehensive testing through software-in-the-loop and hardware-in-the-loop configurations further guarantees that the system performs optimally before real-world deployment. ePPC excels in delivering reliably through both software and hardware redundancy, ensuring continuous operation even in the face of unexpected failures. Additionally, it offers rapid control response times for advanced functions, which are essential for maintaining grid stability during fluctuating renewable energy inputs. The advantages of ePPC extend to its software-based nature, which supports agile development and customization for specific projects. Its model-driven approach ensures accurate and efficient performance by aligning closely with the power plant's digital twin. With its comprehensive capabilities, ePPC not only meets the complex demands of modern power plants, but also provides a future-proof solution for effective power management. Thank you for your attention.